Next, I want to discuss the two fixed span and its assumptions. So when we write two fixed span models, we very often write down this parametric model. And here, note that there's no IT, right? There's no IT. There's only one parameter, a parameter and no subscript. This makes a constant treatment fact. Sometimes some authors will add DIT -1 or DIT -2 to the model. This is called distributed lags. And then you sort of relax this assumption a little bit. You allow the past treatment to have effect on the outcome. And sometimes people in a dynamic treatment facts estimation, they would interact this DIT with a bunch of dummies indicating how many periods you have been in the treatment to relax this assumption a little bit over time. But at least in a baseline model, people estimate this type of a two fixed span model. Okay, so the function form, what are the assumptions? Embedded function form, obviously, you have as fixed facts just like in DID, and then you have constant and contemporaneous treatment facts. Right, the treatment fact is not only constant but also contemporaneous. It does not allow, with this model, does not allow today's treatment to affect future outcome, and you have linearity in covariates, this part. But I don't think this is not that important. I think because you can always, this is a nuisance parameter. You can always use a machine learning algorithm to make it more flexible, like double selection and whatnot. I don't think that's a very strong. That's very important. But I want to put it out there because most people do not use those more advanced methods to select covariates. But I think at the end of the day, in many applications I have seen, the covariates are not doing a lot of work. All right, a lot of covariates are simply noises, so it may not be that important. Okay, so the second assumption is set of assumption. There's a lot of small implications by this assumption. Is strict exogeneity. It says basically the error term. Of course, this assumption is conditioned. It's actually conditioned on the functional form assumption, right? Because when you write epsilon IT, you already accept this model, right? Otherwise, where does this epsilon IT come from? So it's actually on top of each other. Epsilon IT is a orthogonal or a statistically independent of treatment assignment covariates of all time and all units. So all units, right? Here, this is J and S. It's different from I and T. So this basically says the treatment is assigned in one shot. Well, slightly more than that, but I'll explain the details. But mostly you can understand it as the entire vector of treatment is assigned at one shot. And then you have that kind of assumption to be satisfied. This is very strong, but stronger than we normally admit. And this implies, this is very nice because with strong assumptions, we can claim a lot of things. This implies the treatment assignment is orthogonal to the two potential outcomes. Right here, the potential outcome, you only have two versions of, this is really nice because the assumption is so strong. You only have two versions of potential outcome for each IT. The history is irrelevant. With such strong model, history doesn't matter at all because the past treatment does not affect future outcome because you don't remember the past different. The treatment is assigned as one shot, so you don't even need to introduce the notation for treatment as a history of treatment. Okay, so if this assumption is true, the parallel trend assumption is true. The parallel trend assumption is implied by the strict exogeneity assumption. You can do a little bit mathematics. You can see immediately parallel trend of any kind for any potential comparisons between pairs of cohorts is satisfied. Okay, and so how strong are those assumptions? We will digest one by one. Its implications one by one. So first implication or first challenge is that the treatment fact heterogeneity will lead to bias. So we will spend maybe over half an hour or the last hour even on this question. So later we'll discuss this with more details. And second, prevalent parallel trans failures are observed in the literature. And third, strict exogeneity means a lot than what you think. I'll explain what it embeds. And fourth, again, goes back to the question I alluded, I think several times already. What does the fixed value approach imply from a design-based perspective? What kind of experiment you're running in your mind when you estimate a fixed value model? And hope it gives you a causal interpretation. So first, I want to show you some evidence on potential parallel trans failure. So here I give you 4 examples from almost every field of our discipline. First, if you look at the gun control and crime, this is an example from American politics. Using state level data, you run the outcome variable is crime rate, and so the treatment variable is some version of assault weapon ban using state level data, and you draw a difference in difference plot like this, or dynamic treatment effects plot like this. I'll explain how I did it, but most people draw it using interactions with treatment time dummy and treatment group dummy. But I didn't do it that way, but I'll explain on Wednesday how I draw this. Basically, you see a strong pre-trend, downward pre-trend leading toward the onset of the treatment. Can any of you give me an explanation why that may happen? Yeah, she's exactly right. Also, do you want to say anything?
Yeah, for sure. Basically, yeah, it's just that the more liberal states are the ones even willing to do it. But a lot of times they have other demographics that also make them less likely to even have these types of crime, like such as being more rural. So it just kind of confounds things basically, and we don't think those that are basically opting into treatment are like opting in. Basically, it's not as if random.
Exactly. This is basically blue states. The crime rate drops more quickly if you are following the news. Crime rates in a lot of cities are actually dropping. In urban areas are dropping quite fast in recent years, and those states are usually more liberal states, and they're more likely to adopt strict gun control laws. Again, this is plot. You cannot use this plot to say that gun control laws does not have any effect on crime or a casualty because of crime. This is all about selection, and this is the one example of failure of the parallel trend assumption. And this is exactly what I would imagine. Okay, so another example is from a famous paper by Achimoglu and Causal, of course, to be on democratization and economic development. To be fair, they realized this problem. That's why they devote a lot of time. This is a paper published in JPE. They actually use insider control and a variety of different ways to try to alleviate this problem. But I just want to use their data to illustrate if you don't do additional adjustment, you will see something like this. And democratization will actually give you a negative estimate, statistically insignificant if you use proper standard estimation estimator, but nevertheless, a negative estimate of democratization or development. The reason may very well be crisis leads to democratization, right? Fiscal crisis or war leads to democratization, and GDP dropped first, and then the country democratized. So you compare before and after, you have a negative estimate compared with the comparison group. Another example is actually from I use this example in my job talk. The paper is by one of my 3 of my current colleagues in the audience. Quite funny. They're looking at, it's a famous AER paper. They're looking at investigating the effect of WTO on trade. But if you look at data, this is of course not their fault. It's basically the conventional practice in econ, in social science at that time when they published the paper. But nowadays, if you look at the dynamic treatment effects, it's countries or diets, pairs of countries parties are selecting into WTO. They start to trade more, and they have incentive to join WTO to reap the benefit, and then their trade volume keeps going. Right. So if you, so I try to adjust for this trend problem, and the results do hold. But obviously, using the DID, you would not be very confident that the estimate is a treatment effect of WTO on trade. Another one is again by Achimoglu and co-author. They're looking at Team Geithner connection on stock market return. The argument is Team Geithner was, after the rumor that Team Geithner would be appointed by Obama as the Treasury Secretary, a lot of stocks for Wall Street banks increases because people interpret this as being a business-friendly appointment. But if you really look at data, so they look at 10-day, as most event studies do, 10-day into the treatment, the effect is positive. They look at cumulative return, so cumulative return is positive. But if you look at the pre-trends, here, this is not, I want to use this example to show that pre-trend may not be a trend, may not be a monotonic trend. It can be some factors that are systematically different between the treatment and control groups. Here, if you look at a figure like this, you would not suggest that, you would not think this is so different, right? These post-treatment differences are so different because these companies, these stocks are so different from the rest of the market, the rest of stocks in the market. Okay, so I use these 4 cases to illustrate that if you blindly trust parallel trends and estimate to a fixed model, you're likely to make an error. But actually, these days, because this problem is so well known, almost every reviewer will ask you to draw a plot like this if you use a DID design. So I think the likelihood that it's going to happen is much smaller these days. Okay, so then how do we evaluate this assumption? Normally, we would draw a so-called dynamic treatment facts plot. It's also imported from economists. And so there's a bunch of problems with this type of plots. The previous 4 plots are not drawn using this method, but what most people do is to use the one period. This 0 period is first period after getting treated, and use 1 period before, right before getting treated as the baseline period, the baseline category, and dummy out the rest of the periods. And then you interact these dummies with the treatment group indicator. The treatment group is defined as any unit that is treated, that is ever treated during the entire time period. Okay, so and you get a plot, you plot the coefficients in the confidence interval. There's a bunch of problems with these type plots. Recently, this paper showed that because of parametric assumptions, when the treatment effect is actually heterogeneous over time and across different cohort, you have biased estimates. And another problem is that you arbitrarily choose a base category. This may not be a good idea, may or may not be a good idea. There's not much research devoted to this. And the test is unreliable because not only you have a multiple testing problem, but because you chose a arbitrary category in the test against this category, we're not sure what we're testing against. You're not testing against parallel trends, you're testing against whether the other periods are different, that's statistically different from a period right before treatment. This may be meaningful, may be indicative, but there's no guarantee. So there's some problem with that, and we will try to address this on Wednesday. Okay, so I just talked about prevalent parallel trends failure, so we want to address this issue if we can, if we have enough data. Another issue, another conceptual issue is that strict exogeneity is a lot more, means a lot more than we think. This is a paper, a very good paper by Kosuke and Insong, Kosuke, Imai, and Insong Kim. I think 2019, yeah, I think, I'm not sure it's 2019 or 2019 or 2020. It's in AJPS, it's a conceptual paper. And they show that, I'll explain this DAG in a minute, but first I want to put this out there. They show that parallel trend, so you can decompose or you can interpret the strict exogeneity assumption into the following 4 assumptions. One is that there's no unobserved time varying confounding. This is very well known, and they say that it's very well known in the literature. The second assumption is that past outcome do not directly affect current outcome. So no LDD in fixed square models. This is also fairly well known because if you have the so-called Nicol bias, and you need to address that. And people find, by the way, just one word on this. If you use a GMM dynamic panel to estimate this, like this was kind of fashion when I was taught 10 years ago in grad school, and people basically give up using GMM to address this issue because they find the cure is even worse than the problem. The GMM has much worse finite sample error bias than the bias caused by Nicol bias. And when the T is long enough, the Nicol bias actually goes to 0, but the GMM finite sample IB bias it's an IB problem, right? We have a lot of problems with IB. GMM is an IB, and the instrument using lags are very weak. So you have a huge problem with that. So in Acimoglu paper I mentioned, the democratization paper, if you read it, the JP paper, they said, oh, I don't trust GMM. We don't trust GMM. We use multiple lags and we use long time periods with fixed effects. We believe this is closer to truth. I think they're right on that front. If you use GMM, it's actually less trustworthy. Another problem is past treatments that do not directly affect current outcome. There's no carryover, and past outcome do not affect the current outcome. So I'll draw these lines on this plot. So the first, no time varying confounder, basically there's no UIT or other IT that affects. There's no what should I? What parameter, what Greek letter should I use? That's a mu, okay. So that's a mu IT. So this mu IT is affecting both YIT and XIT, XIT being the treatment. X is the same thing. If you don't observe this, of course, it's mu IT, your estimation will be biased. That is very well known. And the second, past outcome does not direct affect, so there's no this link, right? That is the implication of this assumption. And the third one is past treatment does not affect future outcome. So this is this treatment, these arrows represent. And this is also kind of strong assumption. If you run reporting lag, distribute lags into your fixed effects, I guarantee 8 out of 10 times your lagged x will also be significant. At least one of them will be significant, but normally we don't include them. And this, because the treatment effects take some time to reveal itself, it's like gradually takes off. That's usually the case with observational data. And the last one is the most important one. So we don't have a arrow from past y to future and current treatment. We don't have that. And this, I would just, this assumption is the most crucial assumption. I should say that. I think the most ignored assumption in fixed bias models when we use fixed models to draw causal conclusions. Why? Because this assumption is pretty well known, and this assumption is pretty well known. And this assumption can be relaxed if you put distribute lags or relax your model a little bit. So these three are either well known or can be addressed. But the fourth one is a deal breaker. You can, if you have that, you simply cannot use fixed bias or related estimators to make causal arguments. You have to rely on what we call the sequential ignorability assumption. Under sequential ignorability assumption, there's a different set of tools that we can use. A sequential ignorability, under sequential ignorability, usually you don't assume there's a UIT. You cannot assume there's additive fixed effects. So you are facing this trade-off of either addressing time invariant heterogeneity using fixed effects type of methods, or you can condition on all past information, including past outcome, without conditioning additive fixed effects. You choose one of them. You cannot do both. You do both, you have bias. And we're gonna come back to this theme again. This is what I call the two identification regimes: sequential ignorability, strict exogeneity. You choose one of them. Okay, so and to relax 2 and 3, you can block control past treatments, but you have some practical issues. How many distributed lags do you want to use? Do you want to introduce machine learning methods to help you to choose the model, so on and so forth? And not to mention that treatment effects can be may not be constant, right? So even you introduce them, you're imposing a parametric assumption. And to relax 4, you can use instrument variables, but they're hard to find instruments and very bad finite sample properties. Okay, so we talk about what strict exogeneity means. I want to talk a little bit. These 3 and 4 are very closely related. I just want to highlight the difference between strict exogeneity and sequential ignorability, especially what strict exogeneity imply in a graphical way. Okay, so strict exogeneity is, I think Blackwell, this paper we will discuss, and Glean, 2018 APSR, they have a nice discussion on the difference between strict exogeneity and sequential ignorability. So we will discuss that as well on Friday, because they in that paper, they actually advocate for methods under sequential ignorability, because they think, and rightly so, they think the strict exogeneity assumption is too strong. So they propose methods under the sequential ignorability assumption, including the marginal structural models. Okay, so what may be the hypothetical experiment under strict exogeneity? In Matt and Adams' words, Blackwell and Gling's words, the strict exogeneity corresponds to baseline randomization. So you decide your entire vector of treatment status at one shot before the game starts, before Y is realized, right? So here, the crucial difference is that you do not allow Y to intervene in your treatment assignment. Okay, so you decide your treatment assignment before Y is realized, the actual Y is realized. So one possibility, if you think about writing a simulation, this is how I would write a simulation to satisfy this assumption, but also weak enough. So sufficiently weak to accommodate different observational data, but also satisfy this strict exogeneity assumption. Okay, so so I start with alpha I and xi. So x are, so here, sorry, there's a little bit abuse of notation. X are covariates. You have a set of purely exogenous covariates, and then alpha I. Alpha I is individual fixed effects or individual heterogeneity or unobserved individual characteristics. And then based on the alpha I and xi, either observed or unobserved covariates. So this xi can have a t, but this xi cannot be changed by yt. Okay, this xi needs to be, even you don't observe on day 1, it cannot be changed by y. That's the proof. It needs to be strictly exogenous. And then you determine your entire vector of treatment, and then based on x alpha and di, you determine yi. That's your hypothetical experiment. And the crucial thing is that treatment are not assigned sequentially. They're assigned either randomly or one shot. Examples include random assignment within units. So here, as you can see, you allow the probability of getting treated to be different across units. If UI is very big for one unit and very small for another unit, the die will be different. You have a unfair die with a lot of ones, another unfair die with a lot of zeros. That's possible, but within a unit, you need to make that, you need to roll that die randomly, okay? And also this probability can change over time, but this time shock, I forgot to add, you can also add a common time shock, but common time shock cannot be affected by Y. Just to simply put, anything before the treatment cannot be affected by the realized outcome. That's the key. Okay, so if that's the case, if you draw some, just do some simulation, you will see a treatment status like this. But we never see treatment status like this, right? With fixed by models, you never see something like this as random as this. So it means that basically the real data are generated by very different assignment mechanisms. Probably do not satisfy what strict exogeneity entails. Okay, another possibility that satisfied strict exogeneity is actually staggered adoption design that we discussed earlier. This is why I think how these two things connect to each other. You essentially have alpha I, xi, and then you roll a die. So this die determines when you get treated. And then when you get treated, when AI is determined, the entire vector, when the time is determined, the entire vector of D is determined, and then Y is determined, right? And this is, to me, this is much more reasonable for observational data than this random assignment mechanism under strict exogeneity, right? That's why I like staggered adoption. You don't have to run a real experiment to make staggered adoption work. You can, this AI can condition alpha I, right? Some units are more inclined to get treated. Some more liberal states are more likely to adopt certain policies and a priori. But once they adopt this policy, the policy is sticky and they stay there. And that can accommodate a lot of observational scenarios. And that is perfectly fine. That satisfies strict exogeneity. So that is, if you think about when strict exogeneity may work, this is why. So here I want to highlight that the reason why staggered adoption is like a stellar post-child for strict exogeneity is because you from a DGP point of view, you forbid the past Y, you forbid Y to affect D, right? So once D turns on, it's already 1. So there's no chance that Y can feed back to the treatment status. That is one reason. Of course, one caveat that not all staggered adoption is consistent with strict exogeneity. It's still possible that here in those periods, the Y may feed back to D, right? If let's say there's a very famous term, Asher-Felter dip in labor economics. People lose their jobs, they're more likely to join a job training program. Though this is literally D feeds back to Y feeds back to D. Although you may be in a staggered adoption, they start the program, they stay in the program for an extended period of time. So this does not satisfy staggered adoption. Okay, so the subtlety is we cannot tell what assignment is by looking at distribution treatment status. We can make some judgment call, we can make some guess, but it's not sufficient. We need to get closer to assignment process itself. We need to get more knowledge of how assignment is conducted in the real world with observational data. That's the key. Right? That's the as a research designer, that's a question you want to ask yourself first. All right, so we're talking about the weighting problem. You've heard so much on Twitter, at least if you are following. So one seminal paper is, there are a lot of papers on this front, on this topic, but one fairly famous paper is by Goodman-Bacon. This is one person, by the way, 2021, Journal of Econometrics, if I remember correctly. Yeah, Journal of Econometrics. And so what this paper is doing is to decompose two fixed by models to a bunch of smaller DID, well-defined 2x2 DIDs. And so he motivates this paper by saying, correctly, of course, that most pattern applications diverge from the 2x2 setup because the treatments are, sorry, there's a broken sentence, because the treatments assignments are actually much more complicated. And we know relatively little about how two fixed facts perform when the timing of the treatment varies, especially when the treatment status can reverse. And we rely on general depiction of identification assumptions like random intervention, although very often we don't exactly spell out what that implies. So in papers, people say, oh, I assume strict exogeneity is assumed conditional on some factors, conditional on some additive fixed effects and common shocks. My treatment is called random assign. That is what people would write in their paper, but they're not being very clear, as they probably should be, or as we probably should be. I wrote that papers as well, and we do not know precisely how the two-way fixed effects estimates compares to how by using these two-way fixed effect estimator, in what way we're comparing the conditional means across groups, right? Because two-way fixed effect model is a type of ORS, right? It's equivalent to ORS with a bunch of dummies, and we know that ORS is comparing with binary treatments without covariates are comparing conditional average, conditional outcome, or conditional means of outcome, but we don't literally know, we don't precisely know what two-way fixed effects are doing when we don't have covariates. What comparison groups they're making. With DID, it's pretty clear. With DID, we have 4 cells. We're making these comparisons. What this paper does is actually decompose two-way fixed effect to a bunch of DIDs. And we also have limited understanding of the treatment parameter. And we know it's a weighted average of something, but we don't know what that is. And we also cannot evaluate how and why ternary specifications change estimates. For example, if you discretize sorry, I shouldn't say discretize, it's already discrete. We saturate the model a little bit further by introducing interactions between time dummies and treatment group dummies. We find the estimates are quite different. Why did that happen? And there are a lot of other papers that are either precursor to this paper or written at the same time. So that shows basically how competitive this field is. And most of them converge to the same set of conclusions from slightly different angles. Here, I will present you 2 papers that present this problem differently, but you can see the linkage very closely. And two-way fixed effect estimator and the staggered adoption. In this paper, they consider staggered adoption only. Goodman-Bacon 2021, oh, it should be, yeah, 2021, only consider staggered adoption because there's no reverse, do not need to consider the problem of treatment reversal and do not consider the problem of carryover effects, which is ruled out by fixed effects. So we use the same, oh gosh, there's of course, a treatment variable here. Sorry, and the weights on the what he finds is that the weights on the 2x2s are proportional to the timing, group size, and the variance of the treatment dummy in each pair, which is highest for units treated in the middle of the panel. Let me rephrase. So this is not only found by him, but also a bunch of other papers, including the paper by our friend Anton. So they show that in a panel, if you so the weights will be highest for units that have equal number of treated units. And so you have some control, you have some treated, the weights will be higher. And the weights will be higher for periods that have equal number of treated and control units. So in both dimensions, if you have more variation of the treatment, you have more weights. That is analogous to, if you have read Anoro and Sami, they have an ORS paper on. So ORS is a weighted average of individual effects, and the weights will be highest for units that have the biggest variance in the treatment. So this is the same thing. And what the paper shows what this implies with staggered adoption. And one of the main contributions of this paper is to show this decomposition. These two-way fixed effect estimate. Sorry, this is not a square. This is two-way. Sorry, two-way fixed effects. This is just one label. This beta will converge to summation of 3 items. The first item is variance-weighted ATT. So ATT is well defined for each small 2x2 DID. For each small 2x2 DID, you have an ATT. And the variance weighting is for that 2x2 DID, how much weight I give the two-way fixed effect beta gives to that DID, that small DID. And the second term is called variance-weighted common trends, or common trends or parallel trends, the same thing. So this is basically saying if you have parallel trends violation, you have common trends violation, this will be part of your beta. Right? If the strict exogeneity assumption is satisfied, so this term will go. Right? And then the most important term for this paper is the delta ITT. Delta ITT is a change in the treatment effects in time, and this basically makes the two-way fixed effect estimator estimates, not necessarily a weighted average of ATT. And I will show why that's the case. So this is when heterogeneity of treatment effects or treatment effects change over time makes two-effects fact estimate uninterpretable causally. Okay, so we have three terms. The first term is what we want. The third term is what we don't want. And the second term, you can't forget about it because we assumed parallel trends is satisfied. And we will try to understand where the third term comes from. And by the way, even if we do not have the third term, we still have the first term. And this variance weighted, some people may not like it because we don't know what that exactly is. It's not the a uniformly weighted ATT. It's variance weighted ATT. Okay. All right. So to illustrate this, this paper has very good graphics, a graphic representation of the problem. So he introduces three stylized units, or you can think of them as a group of units, or you can think of them as 3 units. Let's just say there are 3 units or group of units. So one is what we call the never taker. I shouldn't say the never taker. This is confounded with IB. So we just call them the untreated group, never treated. They're never treated. And then there's a group that is early adopter. And there's a late adopter. The difference is that they adopt the treatment, adopt treatment at different time. Okay, one is KLK, one is L. Okay, so let's say, it's a simplified, of course, the data may be more complex. Let's say the stack adoption data only have these 3 groups of units: never treated, never get treated, a late adopter, early adopter. And if you apply a two-effects model to data like this, you essentially are estimating a weighted average of these 4 small 2x2s. Okay, so the first one is very easy to understand, which is early adopter compared with never treated or untreated, or the pure control. I call them pure control. Okay, pure control is better. So early adopter, pure control, you have a well-defined DID, and then you get an estimate. Right? This is multi-period DID, but multi-period DID with 1 treatment timing. So we talk about this. The second is similar. So we have a clean multi-period DID with 1 timing L. Let's use red, maybe. Right? So these 2 are very common. These are basically DID. And then we have a third group, which is we use the late adopter as control. This is late, not to be confused with local average treatment effect, but late adopter as control. And then early adopter as treated. All right, early as treated. Okay, this is also fine. This is fine, this is fine, this is fine. So what really problematic is, I think one of our audience asked the exact question, saying in two-way fixed effects, you will actually use the treated data for the early adopter, which is this one, as control. This is Y1, right? This is already treated as controls for the late adopters. You will use the post-treatment data as controls for late adopters. Okay, is that clear? So this is fine if the data follows exactly the two-way fixed model, which is you have maybe some time trend. Time trend is here is linear or nonlinear, doesn't matter, and you have a constant treatment effect, right? And at least the constant treatment effect is the same. The treatment effect is the same over time within each unit. You can allow the effect to be slightly different, smaller or bigger for the early adopter and late adopters, but it remains the same over time, right? If it remains the same over time, this is a legit control. If the treatment effect remains the same over time, is stable over time, you can use Y1 as control for late adopters. But the problem is that it's never the case, right? If you have the treatment something like this, and this comparison will be gives you totally biased estimates for this DID for late adopters. That is where the delta ATT comes from. Okay. All right. Okay. So the paper also shows, as I suggested early, units. This line basically draws the weights for treated and control for each unit. it serves as treated and can also serve as control. And this is the weight, the net difference between weights for each unit being treated and each unit being in control. So for units in the middle, the weight will be the highest. And for early adopters, so this is like basically getting treated very early. Early adopters, this weight is negative because early adopters also serve as control. Maybe erroneously serve as control for others. For late adopters, because you treated, the number of treated periods is very small, so you also don't get much treated. You always serve as treated as control, right? So for ATT, it is those units that is in the middle of the treatment, get treated in the middle of the time window, gets more weight as a treated unit. Is that clear? Okay. So this is about weighting, and what's the consequence of time-varying treatment facts? Time-varying treatment facts will not affect this three group, right? One, two, will not cause bias for these three groups. Will change the treatment effects, right? Legitimately change the treatment effects. That's fine, but will cause bias because of the fourth group. So it will change ATT across all 2x2 DIDs. It will bind estimates from weighted average, balanced weighted ATT, because delta ATT is not zero in the fourth group, in the fourth comparison. And recall we have this formula, and let's say in this case, how to read this graph? We have late adopter. This is the late adopter. And this is the early adopter. Okay, so in this case, both the late adopter and early adopter does not have a constant change treatment effect. The treatment effect grows slowly. This is the, let's say this is the counterfactual. This is our counterfactual. So for late adopter, the treatment effect grows slowly, right? So this is the late adopter's treatment effects, and this is the early adopter's treatment effects. Are you with me? So they're taking off slowly in a linear fashion. However, because in the fourth comparison, you're using, this is the early adopter, you're using the early adopter as the comparison group. So for late adopters, in this small 2x2 DID, for late adopters, its treatment effect will only be this, right? Will be this instead of the correct one. So that's the problem. So the changing of the treatment effects for early adopters bias the estimates for the treatment effect for late adopters. Okay, so he introduced the example from 37 states. The treatment is no fault divorce reforms, and the outcome is female suicide. So the estimate is negative, and this is actually the two fixed effects. It calls the two fixed DD estimate, which is negative. And if you draw a dynamic treatment effects, it's something like this. Then what Goodman-Bacon does is to decompose this estimate. This is the two-way fixed effect. This is two-way fixed effect DD estimate. It's called two-way fixed effect DD estimates into the individual unit level. Some of them are positive, some of them are negative. For those positive is actually the fourth type of comparisons, right? So fourth type of comparisons is the late group as a treatment versus early group as control. So those post-treatment data for the early adopters as control for late adopters. And those treatment effects are actually positive because the effects gradually roll out for late adopters. Can I visualize it? Let's say early adopters is like, in the early adopters, cannot draw. The early adopters like this, and late adopters is like a different color. Late adopter is like this. So your estimate is effect is positive, right? Right, you DID it, you get a positive effect. This is because for early adopters, its effect already dropping, and dropping maybe faster than late adopters. So you get a positive estimate, which is wrong, right? But because for late adopters, it should also be negative compared with the correct baseline. And unfortunately, because these weights are fairly low, the x-axis is the weights. The weights are fairly low. It does not affect the DD estimate, two-way fixed estimate that much. But as you can see, there's a bunch of wrong estimates here. Okay. All right. So in summary, the two-way fixed estimator under step adoption only has a meaning for causal interpretation under strong assumptions, not only common trends or parallel trends, which is this assumption, but also the treatment fact stays stable which is almost impossible. If you ever conduct a DID analysis, you know that's almost impossible for any policy. I shouldn't say any, but for most policy, gradually take off. The effects gradually takes off is a very common thing. And there's a bunch of problems how to test whether the common trends is satisfied, parallel trend assumption is satisfied, and whether test the treatment effects involves over time. And what happens if either of these assumptions is incorrect. And even when it converges to the variance weighted ATT, this may not be what we care about, right? Because it's very hard for us to interpret weights. And why do we care about those middle adopters that have the biggest variation in treatment status? And next we will investigate this from a slightly different perspective. As I said, many people write about this, and Gutmann-Bacon write about this from a DID perspective, decomposition perspective. And the next paper investigate this problem from a individual cell perspective. I show you the treatment status plots, right? Each block, each cell represents one unit, one observation. So next paper investigate this weighting problem from a cell perspective instead of small DID perspective. And this is also a pretty famous paper. So let's denote tau IT as a treatment effect for unit I and time t. And to effects that they show, well, this is almost always true, right? You can always interpret or decompose a ORS estimate as some weights of the data. That is not that meaningful. The meaningful thing is how to give actually a expression of the weight. So they show that you can interpret the two-effects model as a weighted average of tau IT, and tau IT is the treatment effect for units and the treatment condition individually. So this is those treated, and this is the individualistic treatment effect for the treated unit. And this weight is the residual from running the outcome, running the treatment status as the outcome on fixed effects. And intuitively, I can tell you that the weight is higher when the residual is higher. When the residual is higher, the residual is higher when it has the biggest variation. So it's the same thing. It's consistent with the previous result that for units, for observation, I should say units, for observation in that matrix, in that rectangular matrix, for observation that has the highest variation, or highest variance for the treatment, you have the highest weights. So those observations are observations closest to a shift in treatment status, and in periods that have roughly equal size of treated and control groups. And smaller weights to periods with more where more units are treated, and to units where more with more treated periods. And in staggered adoption, the proportion is non-decreasing in time. Late periods have smaller and even negative weights. The negative weights problem is the same as what we see in the fourth DID example, because if you get treated really early in the later periods for early adopters, those observations will be used as controls, right? So the weights becomes negative. Okay, and the problem is the weights can be negative. As a result, even all tau are positive, the weighted average can be negative. So the weighted average is not even a convex combination of the tau, so which can be really misleading, right? This is the minimum requirement that we want for fixed effects. At least fixed effect estimate needs to be a convex combination of the tau, but they're not necessarily the case. Okay, so let me give you an example from the paper. In this, it's really a non-realistic but simple example for illustration purposes. You have 3 periods and 2 units, and then for unit 1, it is treated at period 3, and for unit 2, it is treated for period 2 periods at period 2. And so the two-effects effect estimate is a weighted average of tau IT for these 3 observations. And it shows, if you do the decomposition, you will find that the weights for the blue one is 0.5. This is 0.5, maybe 1/2, 0.5. This is 1, this is 0.5, and this is negative 0.5. These are the weights. Why this is negative 0.5? Because this guy, as early adopters, when it reaches the 3rd period, this observation serves as the control for the late adopters. When it serves as a control for late adopters, so net weights becomes negative. Does that make sense? Okay, so here as you can see, even so we have 3 tau, even all 3 taus are positive, we cannot guarantee this beta, this 2-wave effect coefficient is positive. If this tau increases really fast, because the weight is negative, the estimate can be negative. Right, so yeah, I talked about this. And the intuition is the same as Goodman-Bacon. We use early adopters to control for the late periods for early adopters as controls for late adopters. So estimated effects can be affected by overtime change in the treatment effects. Of course, if these 3 terms are the same number. Okay, so if the treatment effects are constant, it's no problem. So you will have the beta will be equal to tau if the treatment effects are the same. The measure, so the paper also proposes a measure of robustness, which is the smallest amount of heterogeneity needed for a conditional ATT to be up to sign of the 2-wave effect estimate. And if it's very small, then very little, even very little heterogeneity can be problematic. If very large, 2-wave effect can be robust and gives you some efficiency because of the modeling assumptions. There's possible efficiency from 2-wave effects if the effects are fairly homogeneous. So the paper, another contribution of the paper is that it proposes an estimator called DIDM, or DIDM for multiple. So M here is for multiple. I don't know what's the proper name for it. I searched through the paper, there's no formal name, so I call it DIDM multiple. So it focuses, it's like using an RD idea or like an interrupted time series idea. It drops all the observations farther away, one period farther away from the switch. It only uses observations right before and after a switch. So it focuses on joiner. Joiners are treatment status switch from 0 to 1, and the levers that switch from 1 and 0. And then assuming that you can find comparison units for each joiner, the T may be different, and for each lever. So for each joiner, you find this for the same T minus 1 and T 0, 0 as comparison. You're trying to find a small DID, small 2x2 DID. For lever, you find 1, 1 as a comparison. And it constructs local estimates. So imagine you're doing small matching. You match this unit with this unit, you match this unit and this unit. So for each joiner, the joiner is some sum of the before and after, subtract by the before and after for the comparison group. And lever is the same. It's a before and after, subtract the before and after from the 1, 1 group. Okay. There's a bit of notation here, but so as you can see, let me go a little bit slower. So this is 1, 0. This is 0, 0. And this is basically the 1, 0 means that so T equals DIT equals 0, DIT PT plus 1 equals to 0. This is joiner. This is first the joiners before and after minus before. And this is the comparison group 0, 0. There before and after, and then we do a small DID. So this is a small DID for joiner. This is a small DID for lever. And then it takes a weighted sum of both joiner and lever. So it estimates an ATE instead of an ATT. Okay, so they also propose a placebo test where Y changes from T minus K minus 1 to T minus K for the same group of joiners and the levers, and see whether the effects are close to 0 enough. Okay, so what we have done so far today, it's a good place to stop and reflect. First, the parallel trend assumption involves functional form assumptions. It is not scale independent. It is not a weak assumption from a design-based perspective. Second, but this is good enough because at least we know very clearly how the treatment may be assigned cross-sectionally. And second, we discussed 2-wave fixed models assumptions, and it includes constant and contemporaneous treatment effects. It includes no carryover. No carryover is part of contemporaneous. Includes no time varying confounders. It also includes no feedback, which is often neglected by people. So past Y cannot affect today and future treatment. And in addition to that, if you have heterogeneous treatment effect, the prevalence, sorry, so the first two things I just mentioned, if you have time varying confounder, well known, or if you have feedback, then you will have biased estimates. A third problem is that if you have heterogeneous treatment effect, it's often completely ignored. you will have a weighting problem, and sometimes a negative weighting problem if you have strong changing treatment effects over time. And robust causal inference using panel data needs to address these issues or relies on different identification assumptions like sequential ignorability that we will discuss on Friday. And these are the references for today.